And so, yeah, so let's go ahead and get started for our second
Mhm.
colloquium presentation for the semester. And I'm really excited to welcome Dr. Gokila Dorai, who is a new
Mhm.
faculty here at Augusta University. And they received their PhD in computer science from Florida State University in December of 2019 and have been an in-field digital forensics tool development. Your research is in the field of digital forensic tool development for mobile and Internet of Thing devices using machine learning and AI. And
Mhm.
they have collaborated with internal and external organizations, including the National Institute for Justice and law enforcement agencies. And so today, Dr. Dorai will be talking about identification and extraction of content hiding iOS applications. Thank you.
Thank you, Hadi. All right. So thank you everyone for taking your time and joining the session. And I'm Gokila Dorai. I'm a new assistant professor who just started with the School of Computer and Cyber Sciences at Augusta University. And I'm really, really excited and I'm thrilled to meet each and every one of you. It's just quite unfortunate that this meeting has to be virtual. But when I come in, I'm going to make my best effort to contact everyone in person and talk to you and get you excited all about research in this field. Okay, all right. So my today's presentation is going to be on Vault app identification and extraction system for iOS devices. So Vault apps are also called as content hiding apps. So this specific presentation that I'm doing today, it was also recently presented at another venue called Digital Forensics Research Workshop and Conference. So this is one of the top-notch research arenas for publishing any work related to digital and mobile forensics. Okay, all right, let me get started then. So what really are content hiding applications? So content hiding applications, they basically allow users to hide content such as pictures, videos, documents, and other files in a secret location and in a secure fashion on their mobile phones. It is applicable to both iOS as well as Android. That means for both iPhones as well as Android devices, and certainly for all the other kind of smartphone devices. Okay? So why is this particularly interesting for law enforcement? Or why is it particularly interesting in the field of digital forensics? That's because content hiding applications not only help users hide content secretly, but oftentimes they are used to communicate while users are trying to deal with drug dealing, with spying, as well as trafficking, which involves human trafficking, which involves anything like a labor where the communication doesn't happen face to face, but oftentimes in a secret fashion using certain kind of mobile applications. Okay. And the purpose and other purposes of these applications are spoofing, private browsing, that is without leaving any browsing history, content hiding, such as photos, videos, notes, messages, just like what I explained before, and then secret audio recording, password managing, being a decoy, that is, it behaves, the application has a certain kind of user interface, but it behaves in a certain way in a secret fashion. Private messaging as well as censoring. So these are various different purposes of these applications. And Vault apps hide in plain sight, often mimicking other applications. So we have to keep our eyes open for duplicates. So some of the examples of how content hiding application screen might look like, I'm going to show you in a few minutes. Okay, so these are a list of primary contributions from our research related to content hiding apps. So this specific publication is also the first in-depth exploration of content hiding applications on iOS devices. And we have explored the iPhone's App Store, that is iOS App Store, that is from Apple, and we have found several of those applications. So in a sense, several hundred applications. Okay? The capability to do rapid identification of content hiding apps from any app store, including foreign stores such as Russia, India, and China. So this specific publication can actually identify applications from various different foreign app stores as well. Finally, we have provided a lightweight vault app identification system, which has high accuracy and which only uses the text description of applications as advertised in the App Store. And using that, we have built a vault identifier and data extraction system for content hiding apps. Okay? All right. So here is an overview of the system design, how this is being built. So our VIDE consists of two major systems. One is the identification system. The other one is the extraction system or the extraction engine. So the identification system is used to identify vault applications on the App Store. And then we maintain an internal local database with those list of applications. And using this list of applications in our database, we identify what could be the true kind of vault applications that could be running on user devices. Okay. And then further, we did what is called as a secondary classification, that is accurately identifying of those collected vault apps from the App Store, which ones could be true vault applications. Okay. And then in the later stage, we built the extractions engine, that is, if law enforcement has access to any of the user's mobile device, and if law enforcement wants to just directly approach the vault apps that are installed on a user's device and not having to extract data from other applications in the device, because the most secretive stuff is stored inside a vault application, then the VIDE system will use its extraction engine to acquire a logical backup of the phone. And then using the Vault Apps DB that we have built, it can detect the Vault applications that are installed on the mobile device and finally extract artifacts. So artifacts could include pictures, videos, any kind of secret passwords, notes, or any multimedia. It could be an audio clipping, it could be any kind of recording, it could even be encrypted files. So all these artifacts will be extracted, and this three-step phase is altogether done by the extraction engine. And then finally, we generate a report of all the artifacts that have been collected. In this whole system design, we also took care that the chain of custody of the device is maintained. That is, at no point in time, none of the evidences that are acquired from a user's mobile device has been altered intentionally or unintentionally or tampered with. Okay, all right, I'm moving on to how this identification system has been built. So we used basic keywords for scanning the App Store. And some of those keywords are listed here. So this is called the initial scan. So for the initial scan, we have private, sensitive, censor, protect, decoy, privacy, secret, hide, vault, secure, and safe. So all of the 11 keywords listed here were actually used for finding content hiding applications from the App Store. And when we analyzed the kind of keywords that were used most often were secure and private. So both yielded a lot of content hiding applications in our initial collection phase. Okay? And a similar approach was used for identifying applications, which are content hiding applications from Russian App Store, from Indian App Store, as well as from the Chinese App Store, where we use the equivalent translation of these keywords in the local language. Okay? So here is an example of why the content hiding applications they become more interesting to analyze. So when you look at a user's phone, obviously we will be looking at chat or communication-based messages such as SMS or MMS, like iMessages, WhatsApp, Viber, and few other applications. But what you're looking at here is a calculator application. So this application is as such a content hiding application. It behaves as a calculator, but when you key in a certain passcode, that is external secondary level of unlocking this calculator, it actually opens up into a new kind of interface where it can store pictures, it can secretly record videos, it can secretly record audio, etc. Okay. And when you're looking at the user's device, all that you get to see is an icon which looks so much like a calculator and which also has an app name which is pretty deceiving called Calculator Plus. So most of the applications that we looked at, they had any kind of user interface which is similar to a calculator, similar to a gaming interface, things like a notes-taking application, things like a album, which is used to store photos. So all these different ranges of applications where it's very hard to catch that they are vault applications. Okay. All right. Now we are looking at the App Store organization and how exactly we arrived at the web page where all these vault applications could be fetched. Okay. So the App Store is organized into 5 different regions, and Apple uses this App Store called iTunes App Store. There are 5 different regions, and each region has various countries. So there are totally 139 countries. And when you look at each country's or each region's way of organizing the apps, okay? So we'll have various genres. So we have genres such as business, utility, productivity, photo, video, audio, etc. So we have several such genres. Totally, there are 25 of them. And then for each genre, the applications are classified as popular applications based on their usage, based on their rating, and then they are organized from letters A to Z alphabetically. So when we look through all these pages, for each page, there are about 16 such sub-pages. So all these 16 sub-pages, they contain the vault applications, okay? So, or any kind of applications. And then when we scroll through or when we crawl through all these web pages and then look for certain keywords, we can fetch the vault application. All right. And here is a glimpse of all the different regions that you're looking at. So United States and Canada, Latin, Caribbean, etc. Okay. All right. Now we are looking at the initial identification, that is how the initial identification system was used to fetch potential vault apps. As I described in the previous slide, how the App Store is being organized, you can see the appropriate URLs which we used for landing at a specific web page. So for example, in the 4th line of the slide, you can see https itunesapple.com, and you can see that the specific genre that we are looking at is photos and videos. And then we have arrived at this specific application called Secret Apps Photo Lock. And the keyword that we had used here is secret. And we are at letter A, and we are in page 8. Okay. So when we did this process, we were able to go through close to, I guess, 1 million such applications. And when we gathered all the potential vault applications, we basically stored the app's title, the app subtitle, the app URL, and a few other information related to the application. For example, when we actually fetch any information about the app from a web page, so this is a snapshot. At the lower bottom of the slide, you can see the snapshot of what we obtained. So from this, whatever says ID, So ID 49234269, that is basically the app identifier. And this app identifier is a unique number. Okay. So this is based on what we were able to index our database, and we were able to store all the unique Vault applications in our database. Okay. All right, and here is a snapshot of how the internal database that we built looks like. So the data collection, it involved the app ID, it involves the name of the application, a detailed description of the application, and the URL from which this app was fetched. Okay. So this initial scan was then followed by a sequential scan. All right. And then this Vault apps database, it is periodically updated. I'll tell you why. Because Apple as well as Google both were found to be removing applications such as Vault apps so frequently. So today, if a publisher or an app developer is publishing an app to Apple App Store or Google Play Store, 3 months later, you can find that the app has been removed, or a few months later, the app has not been updated and then it got removed. Even though the app has been removed, the app still continues to run on the user device on which the app was installed. Okay, and there are several reasons for an app to be removed from the App Store. For example, the app is not maintained properly by the developer, or the app was found to contain some malware. The app was doing something out of its defined range of functionality. The app was found to be insecure, and many a times we really do not know what was the reason for the removal of an app from the App Store. Okay? And Apple doesn't make the removal reason transparent, and similarly does Google. Okay? Hence, even though an app could misbehave, an app could be a malware, it can still continue to run on a user device. Hence, we wanted to make sure that at least we keep track of all the Vault applications which have been published to the App Store or the Google Play Store in a periodically updating fashion, such a way that even though the app gets removed, we still can keep track of those applications just in case if we have to extract any inculpatory or exculpatory evidences. Okay. So now we also had to do something called a sequential scan, which was followed by the initial scan. So the initial scan, which was followed by the sequential scan, was for identifying the lookup URL and obtaining what was called as the Apple bundle identifier. Okay. So in the previous slide, I was talking about what is called as an app ID. And in this slide, I'm talking about a bundle ID. App ID is basically an identifier which is used to identify an application uniquely on the App Store, whereas bundle ID is the identifier which is used to identify uniquely an application that is installed on a user's device. Okay? All right. And in order to do this, we looked into the lookup URL, and then we obtained the JavaScript file. And from the JavaScript file through scraping, we were able to obtain the Apple app bundle ID. Okay? So here are the results of the potential Vault apps after the initial scan. So we were able to obtain close to 4,77,002 applications from USA. So these were the apps in significant categories. Okay. All right. And then we also had a number of potential applications which we identified. Those are 2,364 such applications. And similarly, when we looked into the Russian App Store, the Indian App Store, as well as the Chinese App Store, we found close to a couple of thousand of applications. And in order to do this, our system was pretty fast. The total runtime that it took for the initial categorization was about 48 minutes and 2 seconds for the US App Store. So this is basically like coming to almost 0.5% reduction in the number of applications, and then when we identified the potential Vault applications. Okay. And when we looked at the apps that were mutually deployed in various different app stores, we were able to find that applications that were in US region as well as in the Russian region were about 1,831 such applications. And then applications that were shared between the US region as well as the Indian region, there were about 2,015 such applications. And then apps that were found in US region as well as Chinese region were found to be 1,836 such applications. Applications which were mutually deployed in all these four regions from the same developers, there were about 1,735 such applications. So now we have gathered all information about content hiding applications. We have a local store of all those applications. Now the next step is to make sure that the applications that we fetched by crawling the web is all true vault applications. So in order to do this and to automatically label those applications in the future, we first had to establish a ground truth. So to establish ground truth, what we did was the 2,300 applications that we obtained from the US App Store, we basically manually labeled those applications, whether they were true vaults or not vaults. So in order to do this, we split it among each other in the team, and then we manually analyzed, we manually looked into each and every application's App Store's page, and then we read their description, we read their functionality. In several times, we also installed those applications if they were free applications and if they did not require any subscription, and then made sure that, excuse me, I do see a chat message, I believe. Okay.
Yeah, no, it's not relevant to the.
Oh, okay, okay. All right, thank you. Sorry about that.
It's okay.
Okay, yeah. So, all right. So the ground truth was established by a manual labeling process. Oftentimes, we looked into the free applications. We were able to go through their web page in detail. And in few instances, we also had to install those applications locally on our experimental smartphone devices and then tested whether they required any kind of subscription, whether they used any kind of encryption, what are their true functionalities like, is their encryption really as strong as they have promised, and things like that. Okay? So once we did all this process, which took us close to about 6 months, and then we were able to arrive at this data set where we were able to establish the ground truth, and we were able to classify the applications as true vaults and non-vaults. So why did we have false positives? Because when we look for keywords such as secure, when we look for keywords such as private, we also ended up fetching some applications such as secure banking applications, and then private banking applications. And then when we looked at this keyword called lock, we were able to obtain a lot of vault applications. At the same time, we were able to obtain a lot of applications which were dealing with smart locks and then things like that. So we did have some amount of false positives. Okay? And then after establishing the ground truth, we were able to train binary classifiers such as Gaussian naive Bayes, support vector meshing, and decision tree classifiers. In order to minimize the false positive values, we also introduced new set of features, and we were able to build binary vectors. In this case, we had about 20 such features. So each of the keywords that we already had used in the initial scan set became those 11 keywords, and then we also had to add few other keywords which define what could be the content of those applications. So as you see, the new features in addition to the old features resulted in about 20 such features, which we also call as the extended feature set. So we used keywords such as private, sensitive, censor, protect, decoy, privacy, secret, hide, vault, secure, safe, photos, videos, etc. So all these together helped us build the binary vector. Okay. So at the end, our label data set contained 2,963 applications. And why do you see an addition of 690 applications? Because we wanted to keep our data set well balanced and not being biased towards vault or non-vault applications. So we wanted to have a well balanced data set to some extent. So we had finally 1,118 applications, which are true vault applications, and about 1,845 applications, which are non-vault applications. Okay. So we later partitioned the data set into training and test set with random seed values, and we used a fourfold cross-validation method. I'm not going to get into the nitty-gritty details of the machine learning in this presentation because of the general group of audience. However, the paper is actually having a lot of additional technical details related to how machine learning or the classification, the binary classification was performed. So I do recommend that if you are interested furthermore in this, please do read the papers, and I'll be very happy to send it to you as well. Okay. All right. So our final results of the classification summary is here. So with respect to the Gaussian knife Bayes classifier with the support of N724, we were able to obtain a precision of 0.73 and an F1 score of 0.81 for non-vaults. And for vault applications, about 0.86 F1. Similarly, for SVM and decision tree, here we have the summary results, and we felt that the decision tree and SVM was doing much better when it comes to classifying later on whatever applications were fetched from the App Store as true vaults and true non-vaults very well. So we had about 92% for SVM classifier and about 90% for decision tree classifiers. Okay, so for the various runs of the fourfold cross-validation, we have also published the results here. And at the end, the estimated number of vault applications from international app stores using the trained classifiers was found to be summarized here. So we have Gaussian knife Bayes, which yielded 1,091 applications from the US App Store, but 1,680 such applications was found in US App Store using the SVM, and then decision tree classifier was able to identify about 1,412 true vault applications. So this is after we trained, we basically tried to use these trained models to further classify these applications into true vaults and true non-vaults. Overall, we were very happy about the SVM. And to complete the analysis, we basically tried to deploy about 8 different vault applications, which had various functionalities, such as storing passwords, notes, multimedia content, such as audio and video, contacts, encryptions, and we were able to recover several artifacts. Some of these used encryption, some of these required paid subscription, okay? And some also automatically sync the data with the cloud, and they were able to remove the local data of the mobile device. Okay? And these things still remain a challenge to law enforcement as well as to forensic investigators, because when the data gets to the cloud, it becomes hard for us to decrack it, especially without the key. Okay? And we also have the app structure being analyzed, and we were able to do it on both jailbroken devices as well as non-jailbroken devices. And we used Linux operating system to basically run our analysis on the jailbroken devices, where we rooted the device, and then we were trying to look into all the processes from the Linux box, and we still couldn't find major differences between what a jailbroken device Vault app might store versus what a non-jailbroken device Vault app might store. Okay. So here is a result or a summary of how all the captured data or the extracted data would be presented to the court. So you can see that we will have all the chain of custody information, that is to whom the device belonged to, how do you identify the device uniquely, when was this evidence being fetched, how many applications were found totally on the device, and how many of those applications are vault applications, and what are the list of vault applications that were detected, and a list of all the artifacts along with the file path and what kind of media file. Everything that we extract would be documented and presented as a report to law enforcement. And then finally, I'm going to play a little video snapshot of how this whole system works end to end.
Content hiding apps, also known as vault apps, safebox apps, or app lockers, are a class of smartphone applications that allow users to hide multimedia and other documents secretly and in a secure way. Some of these applications, known as decoy apps, further support secret hiding by mimicking common apps such as calculators and games, but turn it into a vault app with a specific input. Vault apps are popular in countries all across the planet, with over 2,000 apps being present on the US Apple App Store alone. These applications are commonly used amongst teenagers who use the apps to hide inappropriate content from their parents. The Vault Identifier and Device Extraction tool is an automated software that can be used to both identify content hiding applications and extract the data locked behind the app's code. First, the software's identification system scans for Vault apps by using prior search information obtained from relevant app stores. Afterwards, a logical acquisition of the smartphone is done by utilizing backup data utility tools. From here, VIDE's extraction engine can analyze the data from the Vault app and generates a report. While this software is only available for iOS currently, this approach can be easily extended to Android-based devices as well.
And thank you, and I appreciate any questions from the audience.
Hi, can you hear me?
Hey, hi, Edward.
Yeah, so do you have any more details about how the extraction works? Were you able to break some of the encryption on these secret vaults, or is it really they were just hiding in plain sight and it was through obscurity and you were able to find it somewhere in the device's file tree?
Okay, great. So we were actually looking into the file system and we were able to obtain whatever data was hiding in plain text. In some instances, the extra level of security was also stored in plain text. But when these applications were found to use encryption, we couldn't get to the level of breaking the encryption. And they also used what is called as AES, military level grade encryption, AES. And I'm just trying to remember what other encryption techniques they use, but in most of the cases they use AES, and we couldn't break the encryption.
Okay, so a lot of these that claim to be secret are not actually keeping things all that secret. They're just kind of using security through obscurity.
Right.
And
that is right. Security through
won't...
obscurity. Mm-hmm.
Yeah, okay.
Okay. And the indirect way that they try to store these files, that is security through obscurity, just like how you exactly said, these applications rename the file in a certain way. Sometimes they hide those files from the file system and then they make it hard for us to identify those files. So if we are using exceptionally licensed software such as Celebrite or any other digital forensic commercial tool, they are able to pull everything off of the device and then identify these files. Even in that case, there is a possibility that if those files are kept hidden, or if the file is synced to the cloud and then overwritten or totally removed from the device, then it becomes a challenge for extracting such evidences.
Ah, right. That's why you mentioned that the
Hmm.
cloud sync was a problem, not just
Exactly. Yeah.
because I was thinking because, oh, then it's in some encrypted vault in the cloud, but even if it wasn't encrypted, it's just harder to find if it's moved to
Hmm.
some cloud storage and erased from the device.
That's right. And the authentication key sometimes we were able to find, but it was only valid for 1 or 2 days, and sometimes it was valid for about 2 months. So it was differing from an application to another application. And later it boils down to a crypto problem as such.
Interesting.
Hmm. Yeah.
So I guess some of the apps are doing some things right. Um,
Hmm.
and yeah, it's a technique I hadn't heard of, but very interesting.
Hmm. Yeah. And I would also alert the community that is attending this talk that even though these applications say that they are trying to secretly store your content, in case if it is for an authentic purpose, that you want to store your banking password in a secret fashion, you can see that some of these things are openly available through AWS servers. It's just a plain text URL that you can go fetch a picture from. You can go fetch a notes file as a text file. So just be alert and be cautious when you're using these applications.
Right, because most of them are not actually keeping your data that safe.
That's right. Yes. At least 50% of what we have analyzed, they don't keep your data safe. That's true. Okay. So I'm also looking forward to continue working on this specific research area. I'm also looking into a few other research areas. Um, if we have students or faculty who are interested in further expanding this research, please do feel free to approach me. And there is no specification as to which year or which level of undergraduate program or graduate program the student has to be. I'm more than happy to start working with anyone who has this open-mindedness towards approaching mobile forensics or digital forensics problems.
Hey, Gokila, this is
Hey, hi
Jason.
Jason, how are
Hey,
you?
good. I had a follow-up to Edward's question. Maybe you said
Mhm,
it and I missed it. What
mhm.
percent of the apps use security by obscurity versus actual encryption? Do you know?
Close to 50% of them, they use a
Okay,
security by obscurity. They use plain text passcodes, which you can easily find out in the file system.
okay. Thank you.
No problem. All right. The students, did I lose you somewhere? Do we have any questions with respect to this research area?
Is it available to be viewed somewhere else, like YouTube or something?
Yes, I'll be more than happy to share the paper also. So I will make sure that I share it with Harley. And this video will be recorded and posted later. So other than that, if you're interested in taking a look at the data set, any faculty or students who are interested in taking a look at the data set and who would like to further work on this, we are happy to share that as well.
Yeah, sounds good. You can send it to me, and I'll even add it to the link on the YouTube video for this presentation in the little description.
That'll be amazing.
Available to everyone.
That'll be amazing, Holly. Thank you so much.
No problem. Thank you.
All right. Thank you. So if we don't have any other questions, I would like to thank all the participants. You're all amazing, and this was a pleasure for me to present about it.
Yeah. Great. Thank you. And I think we can stop here. Excellent. Great job. And thank you for such a interesting and engaging presentation.
Thank you so much, Harley.